reporting on the refrigeration cycle results with my teammates Mal Biggs and Joseph Von Morgan. So first, for this experiment, the base objectives are to analyze the refrigeration system, and the main things we'll take out of this, at least for this experiment, will be state properties and coefficient of performance, as well as getting a better understanding of how a thermostatic expansion valve functions. And a little bit of a background, just like what COP means. It's basically the ratio of cooling to the amount of work that you put into the system. So basically, it's how well you can cool a room, pretty much. And it's like it is in the name, like performance, it's a measure of performance. So this is just a basic diagram of a refrigeration cycle, starting with the compressor, moving the hot gas into the condenser, and then a hot liquid to the expansion valve, and then a cool refrigerant into the evaporator, just like a baseline description of how a refrigerant cycle works. And this is the actual experimental apparatus we were working with during the experiment. So section 1, which is I just drew a very squiggly circle around it, represents the compressor side of the refrigeration cycle. Section 2 represents the condenser side. Section 3 will be where the expansion valve is, and section 4 is the evaporator side. And the working fluid, or what we're using to push the fluid through, are section 5s. There's 2 of them, and there are 2 pumps. So a little bit of background on a thermostatic expansion valve and like what it does. So the basis is it cools or controls the refrigerant flow, senses temperature, and it applies basically a pressure balance. Because it does this and it applies a pressure balance across the spring, the evaporator, and the bulb, it basically prevents any like abrupt changes in the fluid that's flowing through it, allowing it to maintain a constant enthalpy across the valve. So this is the result we got for the first case. So power consumed by the compressor was 384.8 watts, and the recorded temperatures of the exits of the condenser inlet and the exit of the condenser was came out to be a difference of 3.6 degrees Celsius. So this is the simple calculations when determining the COP for the first case. So the governing equation is basically just a heat balance or conservation of energy of the system, where the change in the temperature of the working fluid will be equal to the amount of work required in the system, or not the amount of energy taken out of the system. So it came out to be 1,248.98 watts, and when you plug into the COP equation, which basically is the ratio of the amount of energy taken out of the system versus the amount of work you have to put into it, and the -1 there is to account for the fact that just QC over work is the heat pump equation, but we want the refrigeration COP performance, which is the heat pump -1. So that came out to be 2.248 COP performance. So these are the next 3 more slides will be cases 2 to 3, which is our results of all the basic pressure and temperature state values in the system. And using these values cross-match with the tables given in the experimental appendix, you can calculate the enthalpy values for the equation, or the enthalpy values for the system. And then this is just the second case, and this is the fourth case, or not the third case, the fourth case. And with those values and those enthalpy values, we'll calculate the COPs using a different formulation of the equation, which is just relating the same idea, the amount of required work that you put into the compressor versus the amount of heat you're getting out. And this is the pH diagram. This is an example from case 2. So the values on the right, or the enthalpy values on the baseline on the right, are taken from case 2. And PC and PE represent the isobars in the system. And so, got my connection on stack, sorry, explained that before. But these are the sample calculations for cases 2 through 4. So like I said, it's different from the one before, since we had different values, or different given values. So basically, H1 minus H4 is the amount of work required, or the amount of energy you're getting out of the system. H2 minus H1 is the amount of work required to put in the system to make it run. And the 0.4 accounts for the efficiency of the compressor. And so this is using the reference values from case 2, which came out to be 2.24 coefficient performance. And then same procedure for all of them, it did the exact same thing, just ran through all the cases. And these are all the coefficient performances for all cases 1 through 4. And so potential sources of error that I thought of, one, sensors, obviously, like sensors aren't 100% accurate. There's some like errors in sensors and how like close they're going to get to the actual value of the system. 2 would be leakages, because you are working with pipe flow, so there's a lot of fluid moving through. You don't know where leakages come in, and this also can work backwards, like air getting into the system, so it's a two-way street with that. The third one would be assuming ideal conditions, and what I mean by that, like there's going to be energy taken out of the system from the surrounding. There's not much you can do about that. That's just going to happen. So that wasn't accounted for in the calculations. And the last is, I said failed stabilization. That just means like you have to wait for, if you really want to like reach steady state, you got to wait for a long period of time. So when we're calculating the values in the experiment, the values were still fluctuating slightly, not a lot, but they basically made reasonable doubt that they stabilized, but it wasn't truly at steady state if it was, or if it were to be ideal. Oops, that went okay. So in conclusion, just going back to what a refrigeration cycle does, it's an important system in everyday life. It's an effective tool keeping a place cool. And our results were, I say, good, because they all were greater than 1. Less than 1 is bad. That means we did a bad job and the cycle doesn't really work that well. And these are some of the references used, and any questions?
Just one question. You can stop.
Yeah.
I don't need to advise this question.